Unification is the process of determining whether two expressions can be unified, that is, made identical by appropriate substitutions for their variables. As we'll see shortly, making this determination is an essential part of resolution. A substitution is a finite mapping of variables to terms. In what follows, we'll write substitutions as sets of replacement rules, like the one shown here. In each rule, the variable to which the arrow is pointing is to be replaced by the term from which the arrow is pointing. In this case, x is to be replaced by a, y is to be replaced by f of b, and v is to be replaced by w. The result of applying a substitution, it's called sigma, to an expression phi, is the expression written phi sigma, obtained from phi by replacing every occurrence of every variable in sigma by the term with which it is associated. For example, applying our substitution to the expression p of x, x, y, z yields p of a, f of b, and z. Given two or more substitutions, it's possible to define a single substitution that has the same effect as applying those substitutions in sequence. For example, the substitutions x gets a, y gets f of u, z gets v, and u gets d, v gets e, and z gets g can be combined to form the single substitution x gets a, y gets f of d, z gets e, u gets d, and v gets e. And the single substitution has the same effect as the first two substitutions when applied to any expression whatsoever. Computing the composition of a substitution sigma and a substitution tau is easy. Okay, there are three steps. First, we take tau and apply it to the replacements in sigma. Having done that, we join to sigma all pairs from tau which have different variables than those in sigma. Notice that in this case, we did not include the binding of z to g from tau because we already had a binding of z to e in sigma. Finally, in the third step, we delete any assignments of variables to themselves. No examples of that in this case. Okay, now why do we care about substitutions? Well, it's the first step in unification. Say a substitution sigma is a unifier for an expression phi and expression psi if and only if phi sigma is the same as psi sigma. In other words, sigma applied to phi and sigma psi applied to psi produce the same expression. If two expressions have a unifier, they're said to be unifiable, and otherwise they're non-unifiable. So an example of non-unifiable expressions shown here would be p of x, x on the one hand and p of a, b on the other. There's no way to bind x so that it's the same as a and at the same time the same as b. Okay, now although the substitution unifies two expressions, it may not be the only unifier. We don't have to substitute b for y and v to unify two expressions. We can equally well substitute c or d or f of c or f of w. In fact, we can unify the expressions without changing v at all by simply replacing y by v. Now, in considering these alternatives, it should be clear that some substitutions are more general than others. In fact, we're going to enshrine that with a definition. We say that a substitution sigma is as general as or more general than a substitution tau, if and only if there's another substitution, delta, such that tau is the composition of sigma and delta. For example, the substitution at the bottom here is more general as or more general than the other two, since each of the first two can be contained by composing unifier at the bottom with another substitution. And in fact, the substitution at the bottom is more general than the other two in that the reverse does not hold. There's no way to convert either one of the first two into the third unifier by applying an additional substitution. Now, in resolution, we're interested only in unifiers with maximum generality. It's called a most general unifier, or MGU. And it's defined as follows. An MGU sigma of two expressions has the property that is as general as or more general than any other unifier. Now, it's possible for two expressions to have more than one most general unifier. However, even though this is the case, all of the most general unifiers are structurally the same. In other words, they're unique up to variable renaming. For example, P of x and P of y can be unified by either the substitution x gets y, or by the substitution y gets x. And either of these substitutions can be obtained from the other by applying a third substitution. It's not true of those unifiers we saw earlier. Okay, one good thing about our language is that there is a simple and quite inexpensive procedure for computing the most general unifier of any two expressions, provided that there is one. The procedure assumes a representation of expressions as sequences of sub-expressions. For example, the expression P of A, F of B, and Z can be thought of as a sequence with four elements, namely the relation constant P, the object constant A, the term F of BC, and the variable Z. The term F of BC can in turn be thought of as a sequence of three elements, namely the function constant F, the object constant B, and the object constant C. Okay, given that representation, we can describe the procedure in detail. We start with two sub-expressions and a substitution, which is initially empty. We then recursively process the two expressions, comparing the sub-expressions of those expressions at each point. Along the way, we expand the substitution with variable assignments, as we'll see. If we fail to unify any pair of sub-expressions at any point in the process, the procedure as a whole fails. If we finish the recursive comparison of the expressions, the procedure as a whole succeeds, and the accumulated substitution at that point is our most general unifier. Okay, the rules are these. If two expressions being compared, or two sub-expressions being compared, are identical, we succeed on that step. If neither one is a variable, and at least one is a constant, then we fail. If at least one of the expressions is a variable, we proceed as described in just a moment. However, if both expressions are sequences, neither variables nor constants, then we iterate across the expressions comparing sub-expression to sub-expression as just in the same manner as just described. Okay, now what about the case where we have at least one of the expressions being a variable? Right, in this case, we first check whether the variable has a binding in the current substitution. If so, we try to unify that binding with the other expression. If there's no binding, we can give it a binding, but first we check whether the second expression contains the variable to which we're binding it. If the variable occurs within the expression, we fail. Otherwise, we set the substitution to the composition of the old substitution and a new substitution which we bind the variable to that second expression. This will all become a lot clearer when you look through some examples right now. So here's our first example. Consider the computation of the most general unifier for the expressions P of xb and P of ay with the initial substitution empty. A trace of the execution of the procedure for this case is shown here. We show the beginning of a comparison with a line labeled call, together with the expressions being compared and the input substitution. And we show the result of that comparison with a line labeled exit. At each point here, the indentation shows the depth of recursion of the procedure. Okay, so here on the first nested step, we compare the first element of the first expression with the first element of the second expression. Since they're identical in this case, we succeed with no changes to our substitution. We then compare the variable x to the constant a, in this case leading to a binding of x to a. And finally, we compare b to y. In this case, we compose the current variable assignment, x gets a, with assignment of y to b, which produces the joint assignment, x gets a, y gets b. At this point, having reached the ends of both expressions, we're done. Okay, here's another example. Consider unifying the expressions p of xx and the expression p of ay. Here's our trace. The main interest in this case is in the step involving x and y. So at this point, x has a binding to a, and so we recursively compare that binding of y, the replacement, which is a in this case, to y. In this case, we can bind y to a. We compose that substitution with the original substitution to produce the resulting composite substitution. X gets a and y gets a. And again, since we're done processing all of the sub-expressions, the substitution at this point is the most general unifier. Okay, here's an example where two expressions do not unify. Start the same as before. This time, when we compare the second x to b, we get a different result. As before, we retrieve that binding of x, namely a, and try to unify a with b. Since these are two different constants, we fail, and unification as a whole fails. Okay, here's one more example. This one's similar to that last one, except that the second term in the second expression is the functional term that contains y. After unifying the first two arguments, we find ourselves trying to unify x and f of y with a substitution where x is bound to y. Now, in order for this to work, we would have to unify y and f of y. We'd have to bind y to f of y. But now remember back to the condition that I mentioned on variable assignments. We must not ever bind a variable to a term which contains itself. Since f of y contains y, the substitution, the unification process in this case fails, and the unification process as a whole fails. Okay, now you might be wondering why exactly we have this condition that a variable may not be bound to itself. Okay, well, one reason is this. If we were to allow bindings of variables to expressions that contain those variables, it would lead to circular bindings. Now, this in itself is not a problem, though it does raise the question of how many times the substitution needs to be applied. More importantly, though, it can create a situation where the substitution does not actually unify the input expressions, no matter how many times it's applied. Okay, as we see here, applying the substitution does not lead to the same result, and it fails no matter how many times we apply it. The second argument in the second case always has one additional application of f, and so these expressions will never look alike. It's the reason why we check whether variables contained in an expression before creating a binding. And it has a name, it's so important, this condition. It's called the occur check, for obvious reasons. Interestingly, though, not all logical systems do this occur check. Prolog, programming language Prolog, is notable for not performing the occur check, or at least not by default in most systems. Programmatically, it's useful as a way of generating circular data structure, or logically, it can lead to errors, and so in logic, we always do the occur check in resolution.